starting. We're doing section 7.4 today on exponential models and growth. So we did linear models. So in sections 7.1 and 7.2. And by the way, we're not covering 7.3. So in section 7.1 and 7.2, we studied linear models. So we studied linear models in which a quantity grows at a constant rate. Okay, so we're doing in this section, we're doing exponential models. When a quantity grows or decreases by a fixed percent, the situation leads to an exponential model. So here's the situation. This is the same situation as in the book. Let's suppose that a $1,000 principal. A principal is an initial investment or an initial deposit. A $1,000 principal is invested in an account paying 8% interest per year. Okay, so we are going to let T denote the years after the initial investment. And A be the amount in the account. Okay, so initially, T is equal to 0. And the amount in the account is going to be $1,000. After 1 year, T is equal to 1. So after 1 year, the account will have earned 8% of that of the previous amount. And we're assuming that we're not making any other deposits or withdrawals. So after 1 year, it's going to be 1,000 plus 8% of 1,000. So you know that 8% is 0.08. Distributive property, we do this backwards. 1,000 is the same as 1,000 times 1. And this is 1,000 times 1 plus 0.08. But 1 plus 0.08 is 1.08. Okay. I mean, for this matter, that's going to be $1,000. It's $1,080. But that's after 1 year. After 2 years, T is equal to 2. And the amount in the account is going to be the previous amount, the amount after 1 year, plus 80% interest. So that previous amount of 1,000 times 1.08 will earn 8% interest. So 8% of this number is going to be this number times 0.08. So repeating the process. Any number times 1 is the number itself. Factor out the common factor. And that's times 1 plus 0.08. but 1 plus 0.08 is going to be 1.08. Or 1,000 times 1.08 squared. Squared. And I will do one more. After 3 years, the previous amount will earn 8% interest. So that's going to be 1,000. So that amount will earn 8% interest. So the common factor is 1,000 times 1.08 squared. And then this line multiplying by 1. And this is 1 plus 0.08. But 1 plus 0.08 is 1.08. So that's going to be 1.08 times 1.08. That's going to be 1,000 times 1.08 to the third power. So if you're noticing a pattern, any number raised to the first power is the number itself. So that's after 1 year, after 2 years, after 3 years, so after 4 years, now we have a pattern. When t is equal to 4, the amount in the account is going to be 1,000 times 1.08 raised to the 4th power. So I wasn't finding the approximate quantity. I wanted to give you the pattern. So the process So I discussed first simple interest, and in simple interest, interest is earned only over the initial deposit. In this process, the account is earning interest over interest over interest year after year. So the process of earning interest of earning interest on interest is called compounding. And after n years, the amount in the account will be, if we follow this pattern, it's going to be A equals 1,000 times 1.08 raised to the n power. So I'll give you the formula, the compound interest formula. So I just need to open the book. And I'll copy the formula for you. Okay, so there it is. If we invest the amount P for the principal in an account earning a yearly interest rate R, and we compound the interest for n years, then the amount in the account A is going to be P times 1 plus R raised to the n power. We're going over example 1. On the same page. Okay, suppose that you deposit $1,000 in an account that is compounded annually at a rate of 8%. Find the amount in this account after 30 years. Okay, so we want to find A. The principal is 1,000. The interest rate, whenever we do arithmetic with percents, we need to convert the percent to decimal, and we want to find the amount after 30 years. So the amount is 1,000 times 1 plus 0.08. So I'm using the formula above, raised to the 30th power. And I'm going to show you in the calculator how you can do that. Or okay, or we can actually simplify this a little bit. 1 plus 0.08 is 1.08 raised to the 30th power. And I'm going to show you on the calculator how to do this. This is 1,000 times 1.08 raised to the 30th power. And actually the amount will grow. If it's growing by 8%, that's going to grow 10 times more. 10 times what it was. So to the nearest cent, so this problem is about money. To the nearest cent, that's going to be 10,000. $10,062 with 66 cents. So if you want to put this on a calculator, it depends on what calculator you have. But this is 1,000 times 1.08, and then your calculator button is either y to the x. Okay, so you have to, it depends on the calculator, but you may have y to the x, or it may be that. Okay, another example. That's number 6. At the end of the section on page 347. So we have all this description that I'm going to copy. I believe I shared the screen after I did the after I show you how to do it on the calculator, but in exercises 5 through 8, you are given the principal in a bank account, a yearly interest rate, and the time the money is in the account. Assume that no withdrawals are made. Use the compound interest formula to compute the amount in the account after the specified time period. Assume compounding is done annually. Number 6. So the principal is $7,500 invested at or paying 7% interest for 6 years. So that's the principal. The interest rate, 7%. We need to write this as a decimal, and then it's 6. The amount in the account is 7,500 times 1 plus 0.07 raised to the 6th power. To the nearest cent, I'll show you this. That's 7,500 times 1.06, 1.07 raised to the 6th power. And that's $11,000 to $11,255 with 48 cents. So this money, that's going to be to the nearest cent. So the compound interest formula, that's one of the first applications and one of the most important applications of exponential functions or exponential equations. So the compound interest formula is an example of an exponential equation. So this is what an exponential equation is. I'll copy that, and we can use it in other contexts. But this is what an exponential equation looks like. An exponential equation is an equation of the form y equals a times b to the x power. So the variable is going to be in the exponent. So remember, a linear equation has the form y equals mx plus b. An exponential equation has the form y equals a times b to the x. So we're doing example 2. We can use this idea in other contexts, not necessarily for compound interest. This part, I'm going to do example 2, but we can use an exponential equation to model population growth. To do this, we use an initial population instead of an initial bank balance and a yearly growth rate instead of an interest rate. And here's the example. According to the US Census Bureau, in 2020, the US population was approximately 330 million, with an annual growth rate of 0.59%. If this growth rate continues until 2053, what would the population of the US be then? Okay, so initially in 2020, that's going to be the initial year, the population was approximately 330 million, with an annual growth rate of that percent. And what happens if the growth rate continues until 2053? So the principal, or what was the principal, instead of a principal, we have an initial population. This growth rate, it's still a percent. So as a decimal, that's going to be 0.0059. And n, 2053 minus 2020, n is 33. So the population is going to be 330 times 1 plus 0.0059 raised to the 33rd power. And remember, I set this up in million. I'm going to run this to the nearest integer. So this is 330 times 1.0059 raised to the 33rd power. So that's about 401 million. So that's the population. That's approximately 401 million. If a population or a quantity is decreasing, the growth rate is going to be a decay rate. And it's going to be negative. Okay, so we're doing number 15. Okay, so I'll copy that. Those are the directions. And I'm doing number 15. Okay, so we give you a country's population in millions and the population growth rate in 2015. Use this information and an exponential model to estimate the country's population in the specified year. So they give us the initial population, they give us the growth rate, so the growth rate is given as a percent. What would the population be in 2029? So that is going to be P. It's like the principal, but we have an initial population. The rate, this is still a percent. We need to convert this to decimal. And 2029 minus 2015 is 14. So n is equal to 14. And the population, actually, I should not have used the word P. Well, I already did it, but it should have been more like A. So A is 127 times 1 minus 0.0016 raised to the 14th power. 1 minus 0.0096 is 0.9984 raised to the 14th power. And we're going to estimate the population of Japan in 2029. This is 127 times 0.9984 raised to the 14th power. So that's about 124.2 million. Okay, so far in the examples I have been doing, we need to find the final quantity, the final amount or the final quantity A. So what happens if we need to find something else? If we need to find the initial population, or if we need to find the rate, what should we do? We'll see. So I'm doing an example where you have the initial and the terminal quantity, and you need to find something else. Well, when you need to find the rate. So that's the next page. You're given the population in millions of a country in 2000 and 2020. Use the exponential model to find the growth rate for the specified country over this period. And we're going to do this for Vietnam. Okay, so they give us the population of Vietnam in 2000, and the population in let's see, the population in 2020. We're going to find the growth rate R. Okay, so P is 70, A is 97, and N from 2000 to 2020, that's going to be a total of 20 years. And we need to find R. We're going to find R as a decimal. We're going to write the final answer as a percent. So 70 times 1 plus R raised to the 20th power is equal to 97. Okay, to solve for R, we first need to isolate the exponential. So dividing by 70, 1 plus R raised to the 20th power is 97 over 70. If 1 plus R to the 20th power is 97 over 70, 1 plus R is the 20th root of 97 over 70. Now you're wondering, how can I find the 20th root? This is the same as 97 over 70 raised to the 1/20th power. So 1 plus R on a calculator, that's going to be 97 divided by 70 raised to the 120. And I'm going to show you one more time. This is 97. Remember to use grouping symbols. 97 over 70 raised to the 1/20th power. Okay, so that's 1.0164 approximately. Or 1.06. So 1 plus R is approximately 1.016, and R is about 0.016, or 1.6% when you write the final answer as a percent. Okay, so what have we have done models. So we have been using the same type of equation to find exponential models. Now we're going to find an exponential equation in example 5 of page 343. We're going to build an exponential model. So just as money grows exponentially in a bank account, the price of a product may increase exponentially over the years due to inflation. Suppose that in 2015, the cost of a regular tall coffee at Starbucks was $1.50, and that in 2020, the same cup of coffee cost $1.75. We're going to use this data to develop an exponential model to describe the price of your coffee based on the information given, and use the model to estimate what you will be paying for a regular tall coffee in 2030. Okay, so we're going to find a model of the form, find an equation of the form y equals a times b to the x power. Okay, so we know two things, that in 2015, the cost was $1.50. And that in 2020, the cost was $1.75. So y is going to represent the cost, and X, the years after 2015. When X is equal to 0, Y is 150. So let's plug it in. A times B to the 0 power is $1.50. But any number to the 0 power is 1. So this becomes 1. So A equals 150. We have more information. We know that Y is 150 times B to the X power. We're going to use the other point. 5 years later, the cost was $1.75. So A times, or 150 times B to the 5th power is $1.75 or 1.75. So B to the 5th power is 175 over 150. And B itself is going to be 175 over 150 raised to the 1/5. Okay, so B is going to be approximately, let's calculate that. So this is 175 over 150 raised to the 1/5 power. So that's about 1.031. Or you can even say that the growth rate is about 3.1%. And finally, the exponential model is 1.5 times 1.031 raised to the 5th power. So that takes care of part A. Well, I mean, not to the 5th power, not necessarily to the 5th power, to the X power. B, use the model from part A to estimate what you will be paying for a regular tall coffee in 2030. So 2030 is going to be 10, that's going to be 15 years after 2015. And the price is going to be 150 times 1.031 raised to the 15th power. Okay, so that's 150 times 1.031 raised to the 15th power. That's $2.37. So in 2030, the same cup of coffee would cost $2.37 according to this model. Okay, last example. Number 59. It's also about finding the interest rate. Even though we did that already, we're going to do one more example of that. That's on page 349. If $1,000 grows to $1,302 over 6 years, determine the interest rate during this period. So we're going to use again the formula, A equals P times 1 plus R to the n power, where the principal is 1,000, the final amount is $1,000 with $1,300, $1,302, and that's over 6 years. We're going to find the interest rate. And we're going to write R as a percent. 1,000 times 1 plus R raised to the 6th power is $1,302. Divide this by 1,000, and 1 plus R to the 6th power is $1,302 over 1,000, or 1.302. So 1 plus R itself, it's 1.302 raised to the 1/6. Let's calculate that. So this is approximately 1.045. And R is going to be 4.5. As a percent, it's going to be 4.5%. Subtract 1, so R is 0.045. But the interest rate is usually written as a percent, so that's going to be 4.5%. Okay, so this is it. With this, we finish the 3 sections that we cover in the course for this chapter. And thank you for listening.